This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good morning. So in the last lecture we discussed about a common emitter stage with different topologies. In the sense we have got a resistor divider and then we looked at the expression for gain. Then we have got a coupling, not a capacitor. That capacitor we have connected across RE. Then we again looked at the gain. And then we have got different equations without any series resistance. If you don't have any resistance here, that resistance could be due to a source that you connect here coming from a microphone's output impedance or impedance of the preceding stage if you are designing a multi-stage amplifier. So if you don't have that impedance here, the expression for voltage gain equal to minus RC by 1 by GM plus RE. R in R pi plus beta plus 1 into RE. Because here we are getting not just R pi plus RE, what we are getting is beta plus 1 times RE, so that your input impedance is boosted when you have this RE. Then output impedance, there is no change. Then we discussed when we have voltage divider, I have shown you when you have this R1 and R2 for biasing this transistor, we don't have any change in the expression for gain, because this R1 and R2 is not contributing anything except the impedance part. So now your impedance will become, see, R pi plus beta plus 1 into RE. Then what you will be getting is from the small signal, we understand R1 and R2 coming in parallel with these one. Then again R out, there is no change. Then what we did is we have connected a capacitor C1 across RE that we will do when we design a real amplifier. In that case, in the small signal, capacitor is a short, so that the gain, so you don't have RE. RE equal to 0 for signal. Because this AV, this all the small signal gain, means this gain is for the signal. This gain is for the signal, not for the DC. That is the reason you get these small signal parameters. For DC signal, DC bias, you don't have GM. So all these are for the signal. Then for the signal, what happens is when the signal comes here, signal will go through this capacitor to the ground, and your DC bias, the emitter current, that will go through this RE. Because that DC current is not changing, so that the impedance is equal to infinity, because capacity impedance equal to 1 by 2 pi FC. For DC, F equal to 0, so impedance equal to infinity, so that DC will not flow through this capacitor. Capacitor will block DC. so that the DC current IE will go through this resistor and then signal will go through this capacitor. That is the reason here you get R equal to 0. In the small signal you will be shorting this RE, which I have shown in the previous lecture, which is equal to AV equal to minus GM into RC, and then when you short it, your input impedance you don't have RE equal to 0 here, so you get R pi parallel R1 parallel R2 because your R equal to 0 for the signal. So you have to understand R equal to 0 for the signal, not for the DC bias. R out equal to RC. So all these things I discussed in the last lecture. Then we have seen that the expression for gain, expression for the voltage gain AV, that is different when you have different circuits. When you add resistances, gain is not changing, but then your input impedance is changing. But in this case, the gain is changing when you connect a capacitor. Then the question is, do we have a general expression for the gain of an amplifier when you have common emitter topology? For the common emitter topology, if you have got a general expression which includes all the possible capacitors, resistors for the amplifier, then it is easy to find out gain for a particular circuit. And then, so this is an example of an amplifier. And then here, obviously, we don't have the RC, the capacitor here across RE, but without that, this will amplify the signal. So this is an amplifier. It will work in the real world. So this capacitor is called a coupling capacitor, and this is to isolate your DC voltage from the signal what you connect. We will study about this capacitor in the coming slides. So this is called a coupling capacitor. Again, you have got a coupling capacitor at the output. So this RS is coming because of the microphone. So you are going to amplify audio signals from a microphone. So you have connected your microphone here. This RS is due to the output impedance of your microphone. Then that signal will be coming, and then here you already got to maybe 0.7 volt. That is a bias. Then that 0.7 volt will not come to this side because of this capacitor. Capacitor will block that DC signal. And then, so from here only the AC signal will go this way. So your AC signal will pass through the capacitor and come here, and then that AC signal will be riding on that 0.7 volt. But the 0.7 volt you measure here using an oscilloscope. You put your probe here and then ground, then you will see 0.7. But when you measure here, you don't see that 0.7 because this capacitor will block that DC. It will not come to this point. So that is a coupling capacitor. Then again you got a coupling capacitor at the output, because here you might have 1 volt. Because VC, for example, 1 volt, then that 1 volt will not come to here, DC, because the capacitor will block the DC. But the amplified signal is varying with respect to time, so that it will pass through this capacitor. So this coupling capacitor, we will study the coupling capacitor. And then this is an actual circuit that will work in the real world. Then the question is, can we write down gain for this expression for voltage gain for this circuit? Because if we can write down for this circuit, then we can find out for any circuit, just to do some modifications. Then obviously we can derive the expression from the small signal, but you don't have to derive for this subject. So this is expression. So voltage gain equal to minus RC parallel RL, because you got here RC, you got here RL, divided by 1 by GM plus RE, then you are getting plus RS. So this RS parallel R1 R2, so parallel R1 R2, then by beta plus 1 into R1 parallel R2, because your signal is coming, then the signal here is forming a voltage resistor divider. So your voltage is dividing because of this RS, because you are getting some voltage, and then what is happening is this RS is coming in parallel with R1 and R2 for the signal. So that is the reason R1 parallel R2 by R1 parallel R2 plus RS. So this is the expression you will be getting when you draw the small signal and derive it. But again, you don't have to derive it. It will not be asked for the exam or mid-semester test. It is not required. We will provide you the expression for gain, and then we'll ask you to solve something if that is related to the amplifier. And then, so this is a general expression. So if you know this general expression, then you can refer to this general expression and find out required gain for simple circuits. For example, we will do a group work. So this is expression. Then my question is how to find out gain, voltage gain for this one from this expression, because we know for this is the voltage gain is this one for this big circuit, and then for this one what happens? So for this one, yeah, we don't have V V in, you don't have to take into account V in because anyway V in is not here. Then what is the RS for this circuit? So then you can put RS equal to 0 here. So this has gone. When RS equal to 0, then this R1 parallel R2, R1 parallel R2 will cancel out and this will become 1. When RS equal to 0, all these terms will disappear. Then what you have got is you got RL. Here you don't have any RL here. So what is the value RL? What you are going to put in here? 0 or infinity? Infinity, because RL is open. RL is a big value, means open. So then you don't have RL here. So if you put in RL turns to infinity, big value, RS equal to 0, when you put in here, then what will happen is this will collapse to AV equal to minus RC, because RC parallel infinity, big value. So that when you have parallel combination, the lowest value will predominate. So RC will stay there. So RC by 1 by GM plus RE. RE is here. Then RS anyway equal to 0. So this will already gone. Then RS equal to 0. So that this will cancel out and you get this one. See, so if you know the big equation, the general equation, you can write down expression for voltage gain for small circuits. Then how about this one? So here you have got RB, that is equivalent of RS. Just the name is different, RS or RB. Then you have got a current source. It's a DC constant current source. Not because of the transistor. This is a current source somebody connected here. In the real circuit, people connect a current source. We will study later when we study current mirror. Then we have got R1 here, R2 here. From here, somebody connected a capacitor here. Then how to find out expression for voltage gain for this circuit? So this is a circuit. Constant current source is open circuit and capacitor is short in small signal model. In the small signal, you don't have this capacitor. This is short. This constant current source, because this is a constant current source and that is open. So you don't have this part in the small signal. So then this will collapse to see. You got V in RB, V in RB. Then you got RC and then you got VCC and then you got Q1. Then this part is open. So this was gone. And then capacitor is a ground. So this is a ground. So that you got Q1, then from here emitter, then R2 to ground. See, Q1, emitter, R2 to ground. Then from here also R1 to ground. This point is ground now in the small signal, because in the small signal when you draw, capacitor is a short. Then now you can write down. Now you got RB. Yes, you got RB. So this RS means the equivalent of RS. RB is here. Then you got R2. R2 is equivalent of your RE. And then R1 equivalent of your RL. So then what will happen is, but then here you don't have R1 and R2, because here you don't have R1 and R2, means R1 is equal to infinity, R2 equal to infinity, open circuit. Because that's the reason here you don't have it open. Then you will get AV equal to minus RC parallel R1, because instead of RL, you have got R1. Divided by 1 by GM plus RE. Instead of RE, you got R2. Plus then RS. Instead of RS, you have got RB. Then R1 parallel R2 is a very big value. So that RS parallel R1 parallel R2, that is a big value. So that lower value will predominate in the parallel combination. So that's the reason you got RB alone by beta plus 1. Then input impedance R pi plus beta plus 1 into R2. Instead of RE, you got R2 plus RB, because that is coming in parallel, no change. And then R out, RC parallel R1, because you got RC and then R1, that is parallel. So this is expression. See, now we got the expression for voltage gain when you have this topology. So if you know this equation, then we can write down the expression for voltage gain for almost all the circuits. We don't have to write down the small signal. We can just find out what is missing and then substitute accordingly. We can take R1, R2 turns to infinity or RB equal to 0. You can put in the values and then get the expression. So by the way, some of you asked me a question. Maybe I thought I will discuss in the lecture. So how many of you studied feedback here, feedback in your previous degree? Yeah, because I got this question from someone who learned feedback. But we will study feedback from electronics point of view towards the end of this semester. But then the question was, when you have an emitter, So I thought I will discuss in the lecture so that it will be beneficial to all of you. So the question is, so when you have this circuit, emitter, common emitter topology CE, then you are getting RE, and then what you are getting is you got a potential divider, and then this is your maybe Vx, that is your input voltage, and then this is your VB, and then this is your VRE, means that is a voltage across RE. So somebody asked me whether there is a feedback in the circuit. Definitely there is a feedback in the circuit, so we got a negative feedback here. So negative feedback means, what is the concept of feedback? So maybe from the electronics point of view you can understand, you got an amplifier with the gain AV, and then this is your input, and then this is your output. Then that is called open. So this circuit operating in the open mode. Open mode means you got some X and then some amplification AV, and then maybe amplification factor is A times, so that you are getting Y equal to A into X. There is no feedback from Y to X. There is nothing. So this is, we call it as operating in the open loop. There is no feedback. But then if I connect something like this, so you got AV, you got gain A, and then this is your Y, and then this is your X. Then if I connect something back, then I say that you got a feedback loop. Okay, but then when you got a feedback loop, then the question is, you are tapping some from Y, then you may be tapping Y, and then maybe you are taking some percentage of Y. Maybe this is a potential divider, voltage divider, and then you are maybe dividing this Y, and then it will be M times Y. And then here you have two options. You are whatever you are getting, this M times Y, maybe that is equal to W. So you are getting your signal W. So you have two options here. Either you can add X plus W. If you are adding X plus W, then your input is X plus W. You know what I meant? So if you are adding, it is called positive feedback. In the positive feedback, what is happening is you are tapping some signal, and then you are adding to the input signal. Negative feedback. So if it is negative feedback, then what will be is, this is negative feedback, because that is our interest. So if it is a negative feedback, then you got input signal X, then you are getting a fraction of your output voltage, and then so your input here is now X minus W, not input, because that is minus some fraction from the output. So that is called a negative feedback. If it is negative feedback, we have so many advantages. Circuit will be stable. Most of the amplifiers in the op-amp, they have got negative feedback. Then positive feedback, you may add in some cases X plus W, then you are increasing the signal. That is in the case of oscillator is an example. You got positive feedback. Then this is something similar to this one. Why? Because if you write down Vx, so your Vx equal to VB plus VRE. So the VB, so VB is your actually, the Vx is your input, that is equivalent of this X. But then VB is the voltage actually going to the input of the amplifier, so that is equal to this one. So when you calculate VB, which is equal to Vx minus VRE, so that is equivalent of this one. See, X minus W is going to the input of the amplifier, that is amplified. Same way here, VB equal to Vx minus VRE. See, this is output, the collector current is coming to, and then here you are getting a drop, that is because this is a ground connected together, and then so your signal is maybe something like this, connected here, again is a ground connected to the point. See, so this is your signal Vx. See, that is the reason VB equal to Vx minus VRE, which is equivalent of X minus W. So this is kind of a negative feedback. So that's the reason it's got a negative feedback. Okay, that's all. Then coming back, anyway, thanks for asking the question. So how about this expression? So this is what we have seen, V in RB, then we have got RE here. So in that case, it is pretty simple. You got RB, maybe you can try at home, because we already discussed we got RB instead of RS, we don't have R1, R2, and then we got RC, we got RE, then we don't have RL. You can easily write down the equation from this one. Then, now we are going back. So far what we have studied is in the common emitter amplifier, we have not taken into account early effect. We put VA equal to infinity. So VA equal to infinity means our RO, output impedance equal to infinity. So when you derive the expression, then what happens is we have got AV equal to V out by V in, and then we derived an expression for small signal previously. So we don't have RO here. The output impedance RO, we took it as infinity because Early effect. We don't take into account Early effect. But then we derived the expression. But then when we derived the expression, then we found out some issues. The one issue is AV equal to minus GM into RC, and that is without Early effect. So without Early effect, voltage gain equal to minus GM into RC, we can increase the voltage gain. Somebody can argue, I will increase my voltage gain to infinity. Obviously not by increasing RC alone. So they will increase the RC, but then if you increase the RC, what will happen is you will decrease the VC, but it can go to the saturation. Then somebody can say that I will increase RC to the very close to the edge of saturation. Then they will increase the GM, and then they will try to get more gain. But that is not possible in the case of transistor. Or they will say that they will connect here. You can see that when you have 5 volt, you get 161. When you got a 2.5 volt, you get 65. Maybe you can connect 10 volt and get a higher gain. But that is not going to happen in the real amplifier. So this type of expressions we got because we haven't taken into account Early effect. So that's the reason we studied this one. If you don't take into account air, we get some expressions, but that will have some issues. It will be okay to use this GM into RC, and then it will work, but then these are some issues, because this is why the issues arises is because we are not taking into account Early effect. So you can't increase your gain to infinity or a bigger value by varying the supply or GM. By varying the supply, actually you are increasing the GM or increasing the RC. So then the issue is we haven't taken into account Early effect, because when you take into account Early effect without, what will happen is without Early effect, voltage gain equal to minus GM into RC, because here we haven't taken into account RO. So we took RO equal to infinity. So when you take into account the Early effect, what will happen is you have got this RO. So that's the reason this RO, that is coming in parallel with your voltage dependent current source. When you take into account Early effect, we write VA less than infinity. Then the expression will become, because this RO is coming in parallel with RC. So now your expression is minus GM into RC parallel RO. Then, or we can write minus GM into R out. So your R out equal to RC parallel RO. So Early effect, so when you have RO, what will happen to the output voltage gain? It will increase or decrease, because you are getting some RO that is in coming with parallel with RC, the existing value. So whenever you have something in parallel, then your value is actually decreasing. It's not increasing. So Early effect will lower the gain of the common emitter amplifier, and it appears in parallel with RC. So you got minus GM into RC without Early effect. When you have Early effect, you are getting RO, and then when you have RO, it is coming in parallel. Whenever you have got something in parallel, actually the value will reduce. Then Early effect will reduce it. Then the intrinsic gain is independent of the bias current. So I will come to that point. So then here AV equal to minus GM RC parallel RO, and then we define a term that is called minus GM into RO. So minus GM into RO, this is minus GM, that is again small signal parameter. RO, small signal parameter. So this is a maximum gain you can gain with a transistor. So or another way what I can say is, so AV equal to minus GM RC parallel RO. So this is a realistic equation for the voltage gain for a common emitter stage when you incorporate Early effect. So here GM, small signal parameter, RO, small signal parameter, means you can't vary something and get it. Obviously you can vary some current and vary it, but you can't vary anything. So here how can you increase the voltage gain? I want to increase the voltage gain. How will you increase? Maybe one possibility is you put a bigger RC. But then again, there is a limit to the RC. It should not go into the saturation. So if you increase the RC, then what you will get is, when you increase the RC, you will become minus GM into RO. Because RC is big value, then RC parallel RO. When RC is bigger than RO, what will happen is this RO will predominate. Then you maximum gain you can get is minus GM into RO. So minus GM into RO, but GM equal to IC by VT, the expression. RO, output impedance, you already did in your lab, which is equal to VA by IC. So when you substitute, IC will cancel out, then the voltage gain will become VA divided by VT. So VA is the, what is VA? Early voltage. VT is the thermal voltage, 26 millivolt, that is a constant at room temperature. VA is a constant for a transistor. See, then your voltage gain, that is equal to VA by VT, which is equal to minus GM into RO. So that is called intrinsic gain of a transistor, intrinsic gain. So what do you mean by intrinsic gain? So when you fabricate a transistor, the GM, RO, these values, GM, RO, and then your voltage gain is kind of a constant for the transistor. There is a maximum value you can get from the transistor. Like you are manufacturing some transistors. You got a company, you guys got another company, they got another company. Then the question is, you all manufacture the transistors. Then somebody will ask you, okay, for your transistor, what is the maximum gain? Then you cannot say that we don't know that gain. We have to make a circuit and check it. No, you can say the maximum gain you can get with that transistor is whatever you connect outside, that is called intrinsic gain, which is equal to minus GM into RO. And then that is a constant. Why? Because that when you substitute these values, you are getting VA by VT. So that is depending upon the early voltage and the room temperature. If you are operating at room temperature, it's depending upon the VA. So VA equal to 5 volt for modern bipolar transistors. And then VT, room temperature, is around 26 millivolt. So that is a maximum gain you can get for the transistor. So there is an answer. For every transistor, there is an intrinsic gain. So that is called intrinsic. That's the reason we call it as intrinsic. Means that is something inside already decided, and you can't get anything beyond that gain. Maybe intrinsic gain of the transistor, maybe 5 volt divided by 26 millivolt. When you do, maybe you get maybe some value X. Your gain equal to X, or maybe I can tell some number, maybe say we got some 100, just an example, some number 100, that is an intrinsic gain. So when you design a voltage amplifier, you will never get beyond this 100, you will always get below the 100. So that is called intrinsic gain of the amplifier. So if you don't take into account early effect, you will not find out this intrinsic gain. You will think that you will get maximum gain. You can increase the gain. There is nothing setting an upper limit. So when you take into account the early effect, then there is an intrinsic gain. So you should be knowing this one, because when somebody asks you a question, I will give you a transistor, so what is the maximum gain you can get? Then immediately you can say that is called intrinsic gain. And then that intrinsic gain is equal to VA by VT. That is not depending upon any bias current. See, means how much ever biasing you give, because here in the expression you don't have any bias current IC. So you can't bias, you can't increase your bias current, you can't do anything. There is nothing small signal variable parameter here. So this is a constant for modern transistor, for a particular transistor. When you have one transistor, have you found out the early voltage for your transistor? Is it same value at a different IC, or you get different values? You will be getting only one value for one transistor, VA, early voltage. You don't get a different values. You may get a different RO. RO is different for different IC, because VA equal to constant for IC1, you get RO1, IC2 you got RO2, IC3 you got RO3. That value will be different, but VA will be constant, only one value for one transistor. So that is the reason your voltage gain is depending directly proportional to VA, because this is anyway constant, and then that is a constant for one transistor. So there is intrinsic gain that is equal to constant, and then it is independent of any bias, because there is nothing here IC or anything, nothing here. Even you bias bigger or lower, doesn't matter. This is a maximum gain. But in the previous expression, you can see here GM equal to IC RC by VT, means voltage gain you can increase by increasing the IC. See, here you can increase the bias current, and then you can increase the voltage gain. But then this problem is there because we haven't taken into account early effect. So that's the reason here I have written here independent of any bias current. So then somebody can ask, I will increase the bias current, but no, it's not going to help. This is called intrinsic gain, and you can't get the gain beyond this one. Then now we are going to output impedance of the degenerator stage with VA less than infinity. Now the question is, I want to find out the output impedance when I include RO. So when I don't include RO, what is output impedance? So this is my question. So now I am going to find out output impedance with the early effect. Previously we already found out output impedance without early effect. So this is one case. So this is maybe I'll take a simple transistor, not RE. So if you have a simple transistor, so VA equal to infinity. So what is the output impedance? Somebody said 0. Come on, you studied the transistor and then you did lab, you found out VA, and then so what is the output? So VA equal to infinity. So what is here output impedance? So if you got a confusion, just to draw the small signal. Then I am going to connect a test voltage source Vx, then Ix current is coming, and then input I am going to ground, because that is a rule, you have to short the input. So what will happen? So what is Ix here? So Ix will be provided by the GM V pi. Then what is a V pi? So output impedance equal to Vx by Ix. Then you got already the Vx. Then we have to find out the Ix. So what is the V pi? Yeah, because this is ground, so nothing, no current will flow. So that is equal to 0. So then Vx by 0, which is equal to infinity. So then when you don't take into account early effect, your RO equal to infinity. But then when you take into account early effect, what you do is you connect RO here, and then when you do the equation again, then you will get, means we are connecting an RO here with early effect. So then we say VA less than infinity. So then without early effect, for a simple transistor, output impedance equal to 0. With early effect, you get RO. Then now what we are trying to do is, previously we found out, we connected RE here, and then this is your R out. So we already found out with RE what is the output impedance without early effect. Then what is output impedance with RE? What is output impedance? We already discussed it in the previous lecture. Yep. So what is the value? See, if you go back to the slide, we already written several times. With RE, what is the output impedance? R out equal to only RC, because your RO equal to infinity, means if you don't have RC, you got infinity again. So here, if you don't take into account early effect, still with this circuit here, when you take, what is happening is, if you connect RC, definitely RC will come in parallel. If you don't take into account RC, what will happen is here also R out equal to infinity. If you connect RC, definitely RC will come in parallel. Then, so if you don't have early effect, then this R is not going to affect your output impedance. Still you will get output impedance equal to infinity. But then that is not the case. We have early effect. So when you take into account early effect, the question is how will you find out output impedance? So output impedance without early effect equal to infinity means your RO, output impedance equal to 0. Then output impedance we can derive, and then we can get that is equal to R out. So when you solve this circuit, you get R out equal to R0 plus GM into RO into RE parallel R pi. So when you derive, you get this expression R out. In this expression, when you put this RO equal to infinity, means if you don't take into account early effect, what is the value of R out? Because RO equal to infinity, RO equal to infinity, or R out equal to infinity. So if you don't take into account early effect, your output impedance with emitter degeneration or without emitter degeneration is infinity. Then the question is how will you get this expression by solving this one? So that's what I want to see. So I can show you how to get it. So two different ways you can solve it. So I'm going to draw this with RE. So this is your RE, and then so this is a current source. Then this is your RO. Then for finding the output impedance, you are connecting a test voltage source, that is Vx, then Ix current is pumping. So that is the first rule. The second rule is, because we are finding out output impedance, what you have to do is you have to short your input. I have shorted. Now it's up to you how to define positive or negative. So here you can do two ways. I will show you. First I am going to define this negative, this positive. That's what I like it. Because this negative, anyway, it is a ground is there, so I put this negative here. So this is R pi, this is V pi. So if I put positive here, negative here, the current direction will be up. So that is equal to Gm into V pi. Then Ix is coming from this here. What we are going to find out is R out. That is equal to Vx by Ix. Then in order to find out R out, then you should be thinking, when you see the circuit, please don't go and straight away write down the equation. So you think in the circuit, your Ix is coming, then what we have to find out is Vx by Ix. So whatever the expressions means, from that you can write down only two types of expressions. Either you apply Kirchhoff's voltage law or you apply Kirchhoff's current law. So you write down the expressions, then we don't write down the expressions without any aim. So what we do is we write down the expression with the aim, we should get this Vx by Ix form. You know what I meant? So you can do any substitutions to get Vx by Ix. That is our aim. Then when you get the circuit, just think about how the current is flowing through the circuit. So that is another problem. If you don't think it, then you will be in trouble when you write down the equation. The polarity will be different. So here Ix current is coming. Think only logically. Then Gm V pi is coming this way. Then what is the current through this one? Yeah, so then that current equal to Ix plus Gm into V pi. So that is a current through this RO. Then my question is, somebody is going to measure voltage between this A and then B. So what is the voltage between these two? Yeah, so voltage between that one is RO into Ix plus Gm into V pi. Because here is got RO and then Ix plus Gm V pi is flowing through this one. So that is a voltage between these two. Because this, if you don't have RO, then this current source has got infinite impedance. And then, so that is a voltage between these two, because that is the only current going through this RO, so that is a voltage this one. Then we are going to apply Kirchhoff's voltage law. So then Kirchhoff's voltage law, that is equal to Vx, which is equal to, then we already got here this voltage, that is equal to RO into Ix plus Gm into V pi, then plus, so we came here and then this part, then we got this part. So what is the voltage drop across this? So what is the current here? So this point, what is the current? Yeah, because Ix plus Gm into V pi is coming here, then Gm into V pi going up, and then Ix you are getting. Then my question is, what is the voltage here? Yeah, because this R pi and then this Re and R pi both are coming in parallel, isn't it? So then Ix current is coming. So Ix into Re parallel R pi, because both the resistors are coming in parallel. It's a simple case. So you got one resistor. So this is Re, and then your Ix is coming. So what is the voltage here? Ix into Re. Then you are going to connect another resistor here, R pi. Then what is the voltage here? So that is equal to Re parallel R pi into Ix. It's a simple case. So this Ix is coming, then Re parallel R pi into Ix is the voltage when you measure here, maybe at the point C. Then we got the expression. Now we got Ix here, because our aim is Vx by Ix. But then there is one problem. We got a V pi. But then somehow we have to get rid of the V pi, because here I can take Ix out. And then from here I can't take Ix out, because here only Ix is here, but this term doesn't have Ix. You know what I meant? Then somehow we have to find out expression for V pi. So what is expression for V pi?
R pi by here. You can use voltage divider also.
Yeah.
Is flowing through Re parallel R pi. So use a voltage divider.
So think about it. So this is a crude. So that is a, so here we got, see, our aim is taking Ix out, then we got a term. So that's the reason is simple. The small signal is simple. You should know what you are looking for, how to get this one. So now you have to find out expression for V pi. So when you measure the V pi is this voltage, which I already said. What is the voltage? Ix current is coming. When you measure the voltage point, you got the oscilloscope. You measure the voltage at this point and ground. That I already said, that is equal to Ix into Re parallel R pi. So you substitute here. So your Vx equal to Ro into Ix plus then Ix into Re parallel R pi plus Ix into Re parallel R pi. Then you can take Ix from here, you can take it. So I get Vx by Ix, which is equal to Ro into 1 plus Re parallel. So Re parallel R pi plus Re parallel R pi. Then it will become Ro plus Ro into capital Re parallel R pi plus capital Re parallel R pi. See, so this is this expression. So this expression sometimes people simplify in different ways. So one way of simplifying is so they will take, see, V out because R out. So that is your Vx by Ix, and then which is equal to. Then some people what they do is they can take Ro plus Ro into Re parallel R pi plus 1. This is one way of people writing. So here you can see that, so I think I missed the GM somewhere. Yeah, here one GM is there. So here one GM is there because this GM is there. So here one GM is there. Here one GM is there. So here some GM is there. So if you look at this expression that I have here, you can see Ro plus GM Ro Re parallel plus 1. See here, then what we can do is see in this expression you can solve in we can solve in different ways. So maybe I'll start from here. See, because I missed the GM. So this is expression. So Ro plus GM Ro into Re parallel plus 1 Re parallel plus 1. So this one I can write Ro plus, then I can take Re parallel R pi, that is common because here common. Then you get a GM Ro plus 1. So this is expression most of the time you will get it from here. Ro plus Re parallel R pi into GM Ro plus 1. Then here if you can see on the left side what you can see is Ro plus GM Ro into Re plus 1. Why? Because your GM Ro is always greater than 1 because GM into Ro definitely will be greater than 1. That is the reason people write approximately Ro plus Re parallel R pi into GM into Ro. So that is the reason you get this expression Ro plus Re parallel R pi into GM into Ro. So that is the reason we write approximately. So people can simplify in different ways. So this is one form of simplification. So that's how we got this expression. Then, so this expression also I can derive in other way. So other way means I can make this positive and this negative. You know what I meant? So then I can write it down, because if you like that way, then you should be able to get to, even if I spend how much time? Yeah, I got some more time. Yeah, that's fine. So this is Re. So now I am going to write, maybe you got some other group, they don't like putting here negative, here positive. They want to put other way around. So then this is a current source, this is Ro, and then what we have got is we are connecting a test voltage source Vx, then you got Ix. Then some of you don't like putting there negative, so somebody wants to put here positive, here negative. That is fine, you can do it. Then what will happen? This will be down, that is equal to Gm into V pi. Then what will happen is your Ix is coming here, then what is the current flowing through R0? So voltage between this is A, this is B, and again this is C. So what is the voltage between A and B? Or before that, what is the current through Ro? Yeah, then it will become Ix minus Gm into V pi into Ro. So that is a voltage across this one, because Ix minus Gm into V pi flow through this one. Then what is the voltage here? C. So what is the current here? Ix current will come. And then this is Ix current. And then if Ix current is coming, so what is the voltage here? Yeah, so Ix into Re parallel R pi, but then C positive you have grounded, so then you get minus. You know what I meant? Then when you write down the equation, Kirchhoff's law, so Vx equal to the voltage here, that is equal to Ro into Ix minus Gm into V pi, then minus Ix, this voltage, into Re parallel R pi. Then you can substitute value for this R pi, so that is equal to V pi. See, substitute for V pi, because this is R pi, this is the V pi. See, V pi equal to Vc, the voltage here. Then you can substitute the expression. So here what is the problem is the negative sign. Because I put positive here, negative sign, you get a negative sign, you have to be careful with the negative sign. So both the ways you can substitute. So most of the time what happens is I have noted down some students, they start with here and then they miss out this negative here. Then they can't get the answer. So that's the reason you have to be careful which direction current is flowing. So that is the reason I have done like this. Means in the previous case, what I did is I put this negative, this positive, because anyway this is ground, so this is a negative, so that I don't have any negative here. So both the ways you can solve it. Yeah, so when we come back, so that's the reason we got R out, which is equal to RO plus GM RO into Re parallel R pi. We can simplify, because you can take RO common, then we'll get 1 plus GM Re parallel R pi. Most of the time you will find this expression, because they rearrange this one in such a way so that we know that output impedance equal to RO times 1 plus GM Re plus R pi. Means your output impedance without Re. What is output impedance without Re? When you put Re equal to 0, then what will happen is your output impedance equal to RO without any with early effect, but without Re. You know what I meant? So your output impedance when Re equal to 0, when you short it, what will happen is Re equal to 0. Then this term will go, and then you get R out approximately equal to RO. Means that is correct. Your output impedance of a transistor with early effect is RO when R equal to 0. But when you have got Re, what is happening is you are getting RO times some multiplication. So your output impedance is increasing when you have this Re with early effect. So that is the reason we arrange like this, so that we get a feel of, okay, RO times this much is increasing due to this Re. You know what I meant? So that is the reason we are not looking at this way. When you rearrange, it makes much more sense to understand. And then we have got a couple of cases. When we got Re much greater than R pi, what will happen? This R out. When we become R is much greater, then R is very big value, then this will go, R pi will stay there. So you get RO into 1 plus GM into R pi, which is approximately equal to beta into RO. Why? Because GM equal to beta by R pi. Then when R is much less than R pi, then you get 1 plus GM Re into RO. Because then your R pi, you don't have to take into account R pi, because R pi is a big value. In the parallel combination, the lower value will predominate. Then R out equal to 1 plus GM Re into RO. So you will see this expression as well. So when you see this expression, please bear in mind your assumption is your Re is much less than your R pi input impedance. This expression is valid when you have your Re much greater than R pi. And then, so that is output impedance. Sometimes if you, in order to remember that you include early effect, maybe you can connect RO in parallel with your transistor, so that you know that, okay, you are taking into account the early effect. So emitter degeneration boosts the output impedance by a factor of 1 plus GM Re parallel R pi. So that we can easily understand when we rearrange our expression something like this. So that is the reason we rearrange like this. This improves the gain of the amplifier and makes the circuit a better current source. So when you have a current source, as I said, in your transistor is a better current source when the output impedance is 0 or infinity. Your transistor is a very good current source when your output impedance equal to 0 or infinity, because then you are getting IC, VC characteristics kind of a flat. So what I meant is the transistor is a very good current source when your RO equal to infinity. See, when you have RO equal to infinity, you don't have early effect. It's like a straight, means your IC is this one. So this is the VC, and then this is your IC. See, this is straight, means your RO equal to infinity. Then this is a very good current source, because impedance of the current source is, what is the impedance of the current source? Ideal current source. So from here, if you find out the impedance, what is the value? Delta Vx by delta V by delta I, which is equal to infinity here if you got a straight line. So impedance of an ideal current source is infinity. then means that is a straight line. But because of the early effect, you are getting a small slope. So then when transistor is operating as a current source, if you connect a RE, then you are increasing the output impedance of the current source. That is maybe good. When you are using transistor as a current source, maybe you can connect a RE so that you can get a much higher output impedance. We are pushing your transistor to an output impedance that is close to infinity. You know what I meant? I think I'll stop here and continue in the next lecture.
Why this is RO minus, sorry, small RO minus RO times this question.
Please come out again, we'll discuss that.
Yes, yes.
Other lecture we can comment.